On behalf of the Science Coalition, I want to welcome everyone here today. I'm Jack Klein. I'm the Director of Federal Relations for the University of Kansas, and I'm also the President of the Science Coalition. I'll be serving as moderator and your host for our discussion this afternoon. It is truly an honor to be here with this great group of researchers, rising stars in the respective fields of study, and representatives of the 2016 class of PECASE winners. The PECASE, or Presidential Early Career Award for Scientists and Engineers, is the highest honor our nation bestows on science and engineering professionals in the early stages of their independent research careers. The award reflects the importance our government places on encouraging and accelerating American innovation to grow our economy and tackle our greatest challenges. As President Obama said in announcing this year's awardees, each of you is an example of the incredible promise and ingenuity of the American people. Please accept our congratulations as well on this prestigious recognition. Before we start, I'd like to ask each of you to introduce yourself and briefly describe the nature of your work. Jordan, I'll start with you.
Hello, it's a pleasure to be here. My name is Jordan Green. I'm an associate professor of biomedical engineering, material science and engineering, ophthalmology, oncology, and neurosurgery at the Johns Hopkins University School of Medicine. With my other hat, I'm also the co-founder and CEO of Asclepics Therapeutics, a Baltimore biotech company. And my research interests are in using biomedical engineering approaches, biomaterials, and nanotechnology to innovate new types of therapies for different diseases, including cancer and causes of blindness.
Hi, my name is James Rondinelli. I'm an assistant professor at Northwestern University, and I'm a materials scientist, and my research focuses on establishing structure-property relationships of materials, so understanding the structure of materials at the level of atoms and electrons to design and predict the properties of new materials which haven't yet been made, largely focusing on electronic and optical materials found in everyday devices.
Great.
My name is Erica Wolf. I'm a clinical research psychologist at the National Center for PTSD at VA Boston Healthcare System and an assistant professor of psychiatry at Boston University School of Medicine. My work is broadly focused on genetics and epigenetics of post-traumatic stress disorder and related trauma-related disorders. And we've been particularly looking at the idea that individuals with PTSD may be aging at an accelerated rate.
My name is Dave Paglerini, and I am an investigator and director of metabolism research at the Morgridge Institute for Research and an associate professor of biochemistry at the University of Wisconsin-Madison. My group studies metabolism and metabolic diseases. In particular, we study something called mitochondria, which are tiny structures inside all of our cells, which help convert all the things we eat into a common energy currency for the entire body to use. We don't really understand how they work, though, and when they malfunction, some 150 different diseases can arise. So my group fundamentally studies how mitochondria work as a first step to understanding how to treat them when they malfunction.
Hello, I'm Erin Carlson. I started my independent career at Indiana University, but I've recently moved to the University of Minnesota. I'm an associate professor of chemistry. My research group is very interested in how to find new molecules to treat infectious disease. So what we think about on a daily basis is how microbes actually interact with one another and with their hosts, such as us, and how we could try and prevent that interaction to create new therapeutic agents.
Hi, I'm Gijs de Boer. I'm a research scientist at the University of Colorado's Cooperative Institute for Research in Environmental Sciences. And people often tell me I have my head in the clouds. It turns out they're right. I study clouds in the Arctic. We use a variety of tools, unmanned aircraft, long-term observatories that are all around the Arctic to make measurements of the properties we need to better represent clouds in climate models. Clouds have a big impact on how energy is transferred to the atmosphere, which ultimately plays back on things from sea ice, glaciers, and how plants are growing. So that's what I do.
Hi, my name is Tessa Hill. I'm an associate professor at University of California, Davis, and I'm also associated with Bodega Marine Laboratory. I work on climate change in ocean systems in the past, present, and future. One of the things I'm working on is a process called ocean acidification, which is a chemical change that's happening in the ocean due to our human impacts. And it influences many of the animals in the ocean, including things that we like to eat, like oysters and mussels. And so I work on that problem.
My name is Marcelo Gueros. I'm an assistant professor of astronomy at Columbia University. I'm an observer, and my observational interests are in understanding the properties of stars, and specifically stars that are like the sun and a little bit smaller. And in that process, figuring out what the odds are that the planets that orbit them, that we're finding now are very common, are suitable for sustaining life. I also run a Bridge to the PhD program for underrepresented minorities, and one of our graduates this year is actually going to be moving to Tessa's lab in the fall, which is an amazing coincidence.
Lucky me.
Hi, I'm Jennifer Mixes-Olds, and when I was nominated and selected for this award, I was with the Applied Research Lab at Penn State. Just last week, I've transitioned to the University of New Hampshire. At Penn State, I was co-director of the Center for Marine Science and Technology and a senior research associate and associate professor in acoustics. And my research focuses on using acoustics as a tool to study life in the ocean. So passively listening and actively using acoustics to sense fish and plankton, we're able to look at ecosystem type questions about how different parts of the ecosystem are interacting. And the hot topics in my field that I'm working on right now are looking at the effects of sound on marine life, which is very important to ocean users like the Navy and the seismic oil and gas industry, and looking at how marine life responds to environmental change.
Hi, I'm Aaron Roth at the Computer and Information Science Department at the University of Pennsylvania. And one of the things that I study is data privacy. So if you've got a smartphone in your pocket, it's likely uploading every minute your physical location. If you've got a Fitbit, it might be uploading your heartbeat. If you use a Facebook, a social network like Facebook, you know, there are data sets that have all of your social connections on them. And these are hugely important for science, but using them is difficult because there are obvious privacy implications. And my research focuses on how you can usefully analyze large data sets like this while provably protecting the privacy of the individuals within them.
So my name is Alon Gordetsky. I'm an assistant professor at the University of California, Irvine in the Department of Chemical Engineering and Materials Science with a joint appointment in the Department of Chemistry, and I also have an affiliation with the Exercise Medicine and Sports Sciences Institute there. So our research is primarily focused on cephalopods, which are squid, octopus, cuttlefish, and using those animals as inspiration for designing new materials for renewable energy applications, biological electronics, and camouflage. So one of the more fun projects that we have in our group is basically we're trying to make something that works like Mystique and X-Men, except that will work in the infrared to essentially shapeshifters, if you will. It's one of the more ambitious things we're going after.
Fantastic, thank you. Now we know who you are. I'm going to ask our colleagues from the press to introduce themselves and to indicate who they're representing today.
Hi, I'm Jeff Nervous with Science Magazine.
Jeff?
John Fury, I'm columnist for The Hill.
Great. Welcome. I'm going to start out with a question to Tessa. What is the most radically different or paradigm-changing aspect of your research? And what does that mean for the average person?
My research focuses on human impacts on the ocean. And as it turns out, we're having very large impacts on the ocean. And they absolutely affect people. They affect both our enjoyment of the ocean, whether you like to spend time traveling there or walking along the beach or traveling somewhere to go see the ocean. But they also affect the food on our plates, and that also means coastal economies and family businesses and the economy of many of our coastal states. And so for me, I'm not sure this is paradigm shifting, but I think absolutely our understanding of the degree to which we are impacting the environment and the choices that we need to make to start turning that course around is very important.
Absolutely. Erica, you mentioned you're doing research with PTSD. Could you tell us how that would impact, say, the average person who is suffering from that?
Sure. Well, a lot of the work on post-traumatic stress disorder so far has really tried to focus on what's the neurobiology of PTSD, what are the predictors of neurobiology, of PTSD rather, and we're trying to flip that question a bit and say what are the health consequences of post-traumatic stress disorder? What kinds of changes to the body at a cellular level do these psychiatric symptoms cause? And there are pretty substantial symptoms that can range from premature development of metabolic syndrome, autoimmune and neurological disorders, premature cognitive decline, and neuronal decline, and possibly even premature mortality. So we're trying to understand what is behind that accelerated aging process. So we think that this has the potential to really help the individual veteran as we sort through this.
Fantastic. Marcel, how about your research? What is a paradigm-changing impact that may be on the horizon with the type of work you're doing in your observatory?
I think astronomy is in many ways a perspective shifter for humans. When you start to think a little bit about astronomical scales, you realize both maybe how insignificant we are, but I like to turn that a little bit and say how amazing it is that we're around at all, that we can grasp these scales, and that we can interact, even if passively, with the universe in the way that we do. So I think the time we're in now is particularly exciting from this perspective because we're coming closer and closer to the day when we find another planet that is more or less identical to Earth's, and pushing on this question of how common life is elsewhere in the universe. And I think if you spend much time thinking about astronomy, you realize both that many of our day-to-day problems are sort of trivial, but also essential for us to solve at some level because of that, because of our fragility relative to the space around us.
Right. Alon, renewable energy is being discussed in countless conversations on Capitol Hill. Tell us a little bit about your research with do I have it right, the octopus, squid, cuttlefish research that you're doing? How will that impact the average American in the years ahead?
So we're actually, one of the applications that we're working on is clothing related. So we're specifically making a material that can help control how you exchange heat with your surroundings, drawing inspiration from octopus, squid, and cuttlefish. So for example, as we're all sitting here, we're basically radiating heat in all directions. But if you had a material that could trap the heat to keep you warm when you want it to be warm, and release it on demand, to keep you cool when you want it to be cool, well, that could have a huge impact on how much energy we use or the cost of essentially keeping a building at a certain temperature. And so that's one of the ways that we want to really have an impact on people's daily lives and give them something that's inspired by basic science, but that can also change their comfort on a day-to-day level, essentially.
Aaron, it looks like you want to jump in. Tell us about your research. Sure you do.
Sure. So one of the exciting things that we've done recently is we've figured out how to use these technologies that we've been developing over the past decade for data privacy in order to ensure statistical validity in scientific research. So there's been a lot of hand-wringing recently about sort of a reproducibility crisis in science. If you take a medical journal and flip to a random page, then more likely than not, the study that you've put your finger down won't be replicable. And one of the reasons for that is that the statistical techniques developed for hypothesis testing, say, are designed, to be used in the scientific method as you learned it in high school. So first you come up with the hypothesis you want to test, only then do you look at the data, and then you test it. But in reality, people share data. When you actually see the data, you think of new hypotheses to test, which you should. You're learning from the data. But standard statistical techniques do not let you test hypotheses on the same data that you use to develop them. It turns out that techniques that we've developed recently in the world of data privacy can be used to reuse data both for formulation of hypotheses and for testing while having provable statistical validity.
Fantastic. Who wants to jump in here? You just received this presidential award. Tell us about your research and how it's going to impact Americans.
It was interesting. Alan made the comment about developing these techniques to harness radiative energy and kind of control systems, and the clouds do that in the atmosphere. You know, clouds work to reflect energy coming in from the sun. They work also to trap infrared energy that's being radiated by the Earth. And so we really need to understand this to know how clouds are evolving, how they're impacting the climate system, how they're impacting sea ice, glaciers, et cetera. And the work that we're doing is using unmanned aircraft, drones, to get a new perspective on the atmosphere and on these important quantities. I think oftentimes these platforms get a bad rap. You know, they're used in ways that some people really don't like to hear about, but they're also used for good. And this is one of the key examples of how unmanned aircraft can really provide some great perspectives from a scientific perspective. So.
Fantastic. Aaron?
Great. One of the things that is really exciting to me right now is thinking about how we can keep expanding on our understanding of nature to make new therapeutic agents. So the way that infectious diseases have been treated for many decades is using molecules that nature has generated. And unfortunately, most of those treatments, there's now resistance that has arisen to them. And so the work that my lab is doing, that's funded by the National Science Foundation, is to develop new ways to explore the molecules developed by nature itself. And so if we think about the way that these molecules might have been inspired, we think of those that have been used in traditional Chinese medicine for thousands of years. My lab is trying to develop ways to understand what are the actual components of those natural sources that could be used as drugs.
Fantastic. James, tell us about your research. What's radically different?
So I'd like to go back to the energy issue where my group is looking at materials which could lead to low power, more efficient electronics. And this impacts the average consumer in that they want to charge their device less. In terms of the military, and this is the support from the Department of Defense, we're trying to give our soldiers tactical sort of energy independence on the field. And so the idea is to use mechanical energy and convert that to electrical energy. And so that's an active area of research in my group. Yeah.
Jordan?
So in terms of the theme of infectious disease and also nature-inspiring design, some work in my group, we're really interested in how we can create biodegradable particles that then mimic the way the immune system works, and to be basically the generals of the immune system, to train the immune system to recognize cancer and then to go after the cancer. And so the idea is that in the near future, it's the kind of thing where instead of having different kinds of medicines, it could be more like poisons that go through your body, causing a lot of toxicities. You could instead have your immune system harnessed to just go after the tumor wherever it is in the body. And so there's a lot of great work in this area on ways to stop the immune system, ways to stop cancer cells from preventing the immune system to work. And some of the work we do is that we make these particles to then mimic the way dendritic cells or antigen-presenting cells, the generals of the immune system, work, to give them the instructions so that you can inject those particles into, in the future, we do in animals, but in the future, a patient, and then train the immune system, harness it to go after those cancer cells wherever they are and just selectively destroy them. And I guess the other bigger trend that's going on in general medicine is sort of this move to precision and just to stratified and then personalized, to really look at disease for that particular patient with the specific mutations they have and get to the underlying cause of the disease rather than treating maybe symptoms of the disease.
So I hear a lot of passion in your voice. Tell me, what motivates you to do this type of research? What's behind it? Dave, tell me what's at the core of your research in terms of what gets you up in the morning and says, this is what I want to do?
I think as scientists, you have to have a few different motivations. And I think, first, a real belief that the time and effort you're putting in the long run really are going to help people. And secondly, though, that could take careers. It could take many careers. And often, day to day, science is a lot about failure. I think in the more immediate sense, you just have to be passionate and motivated by the idea of discovery. Just the same way kids are excited about science, I feel like a kid in the lab often. And third, when you first start in science, you enter in a laboratory and it's just you and your ideas. And then soon, other people start showing up, graduate students and postdoctoral fellows. And then it really becomes fun because you realize you have the opportunity to teach and to mentor and to train new scientists and instill that same kind of passion in them. So it's all three of those for me. And it's not uncommon for me to get emails from parents saying that my son or my daughter has been diagnosed with something called a mitochondrial disorder, and there doesn't. What do I do? There doesn't seem to be much in the way of therapy, and it's true. So in the long term, I'm really motivated by the opportunity to come up with real therapeutic options for rare metabolic diseases. And we're in time and science, so I think that's becoming very possible.
Fantastic.
Exciting.
Fantastic.
Jennifer,
yes.
Yeah, I'd like to jump in on this one. And one of the things that motivate me to do what I do related to ocean sound is that I like to see that work that I do and my colleagues do create science upon which regulatory agencies and policy is made based on science as opposed to the precautionary principle. Back in 1996, whales were washing up on the beach in possible relation to Navy sonar use. And so that sort of created my field. And ever since then, policy and regulation has really been precautionary and very restrictive for ocean users and not based on the best available science because there wasn't a whole lot to base it on. So doing the science and looking at the impact of ocean sound on marine life has been very helpful in helping to provide information upon which new policy and regulation can be built. And this is really important because if our Navy is trying to think of the right word. If our Navy is charged with our nation's defense, they need to be able to do their job, but they also have to do it in an environmentally compliant way. And so having science to guide them is very helpful for all of us. Same thing with the oil and gas industry. They come under a lot of scrutiny because of the sound produced by seismic air guns. And again, the precautionary principle is applied to their activities. So in order for them to be able to do their job and provide the best energy to our nation, they have to be able to operate in an environmentally compliant way. And so some of the work that I do now goes into those new policies and regulations on what is healthy for the environment.
Right, right. Who wants to jump in? What motivates you to do this type of research?
Sure. Let me
Aaron.
So I'm sort of really do basic research in that I'm a theorist. The usual outcome of my scientific production is a theorem, and it seems sort of obscure, and what motivates me honestly is the joy of discovering new things. But I think one thing that's important is that we shouldn't get carried away with immediate applications, which are applications are of course wonderful, but the importance of funding basic theory is that you don't know what's going to be important next year or in 5 years or in 10 years. And in my own short career so far, there have already been sort of fortuitous applications, things that I was studying basically because of their mathematical beauty turned out to have applications to sort of false discovery control and empirical science and data privacy. And this is one of the main reasons why federal funding is important. I'm funded by the National Science Foundation, and they're one of the primary organizations that funds basic research without sort of requirements that every 3 months or 6 months you sort of report on concrete progress. And it's important to have some of that.
Erica, what worries you as a researcher? Are there things that you worry about in terms of research in the future today in the United States? Are there concerns that you have?
Sure. Well, certainly the funding climate is something that can be very difficult for all of us. I have colleagues who have lost their positions because they weren't 100% covering their salary from some federal government agency. And so that can be very damaging because you're losing lots of good scientists and lots of good research and potentially cures and better understandings of all kinds of, in the case of where I'm working, psychological disorders and other health conditions. I have funding currently from the Veterans Administration, a merit award, and from the National Institute on Aging. But with my NIA, the aging grant, the first time I submitted that, it scored really, really well, did not get funded, not even close. Had to take a resubmission and get it down into the 3rd percentile for it to get funded. So that's a pretty low funding line there.
Yeah.
It's challenging.
I see heads shaking. Other folks concerned about this? Marcel?
I think one of the things that perhaps isn't quite understood about funding is that really when you're talking about funding dollars, you're talking about people. And when budgets are flat or cut, what you're really saying is you can't train as many people as you need to train. And the impact of that is felt immediately by all of us, but by the nation, it will be felt within a decade or 15 years or however long it takes for those people that you're not training to go into some other area of the workforce and be missing from the STEM community. And so I think that's something that worries me a lot, because the impact isn't necessarily today, but tomorrow it will be significant.
Tessa?
Can I add to that? I'll just say as a climate scientist and oceanographer, I would say we are having an all hands on deck moment in this field, because the problems are so large that we really need to open the doors to everyone who can possibly work on developing solutions and developing basic information that we need to have to make good decisions. And I will just echo what Marcel said, which is that in order to do that, we need to be able to support people, and we need to be able to support a very diverse range of people with different ideas and different backgrounds to come into science. We need them.
Erin?
And I think to add on that, I mean, what we're talking about here is answering really big, hard, important questions. And to be able to do that, there has to be a sustainable model for funding. Because if you really want to ask the big questions, you can't do it in a year, but you need to have a plan for how you're going to do it 10 years from now. And so without stability in how we fund our research, it's extremely difficult to really take those risks and ask the biggest questions that you can.
Alon?
So I just want to touch on a few things that people said. I think one of the things that motivates me is training, and teaching students, as I'm sure that's true for many of us as well. And so that's really the most fun part. And you need funding, in order to make that possible. And then, as was just said, you want to go after big problems. So you need agencies that will fund you to work on the big ideas, the risky stuff. So a lot of my funding has come from the Air Force Office of Scientific Research, who have really helped fund the fundamental side of my work, which now, the Advanced Research Projects Agency Energy came in and helped us transition that more towards the applied end. So it runs all gamuts. But in both cases, I really came in with just a crazy idea that wasn't working yet, and they were willing to go after the risk and say, if this works, it will be amazing, we're just about to start kind of showing the fruits of all that labor, from these difficult to fund things that would not have been possible without the agency's I guess forward thinking.
Right. James, it looked like you wanted to jump in.
Yeah, so related to the funding situation, I just wanted to comment on the administrative burden to having a federal grant. And so while accountability is incredibly important, a lot of our effort, for me, it's something like 30% of my time is spent on reporting requirements. And there must be a way to strike that balance between accountability and allowing, investigators to really focus on the science. And so I think that's something that's incredibly difficult for junior faculty who are trying to both establish themselves, develop, frontier science, and, receive this federal funding.
Jordan?
I also wanted to comment on sort of the aspects of with Americans' workforce, with training the next generation of innovators to really create jobs and boost the economy and create all the innovation for America to be a leader in so many ways. And so just like how in university labs are very dependent on government funding from basic research to applications, there's also grant programs for small businesses to encourage innovation. And these come from NIH and NSF, SBIR grants. And they create jobs. And they create jobs that are very information-driven and innovative, and those are things where the funding lines also used to be where excellent proposals were funded, and now excellent proposals that a panel of experts, of scientists and business people say this is excellent, and there just isn't the funding to fund the excellent proposals. And so that's something that I think is being a block on the from unleashing all the creativity and entrepreneurship and growth that can happen from these technologies. The other side with the workforce, I would say, is that I see at Johns Hopkins, for example, the world's brightest students are coming to be educated, and so there's a lot in the U.S. and there's a lot from outside the U.S. And these are very smart, innovative, creative people. They come to the U.S. for education, for their undergrad, for their graduate, their PhD, their MD, and they want to stay here, and they want to create companies, and they want to be academics, and they want to do all these things. Except what happens is their status runs out, and then they have to go back home to India or China or somewhere else. And so I think if there was policies where with a PhD in a leading research organization, you have sort of a shortcut to a green card if you want to stay here and contribute, that would make a lot more sense than having the next, Bill Gates go back somewhere else and then do that there instead. Likewise, a lot of those countries, especially in Asia, are really redoubling their investment in science and technology. And they're headhunting academics from the U.S. over there. They're really building their base. And then meanwhile, we're just flat on a lot of these funding measures. And I think that's something that it's really shooting us in the foot, because this is the engine of growth and productivity that we've enjoyed as a country. And now we're cutting off that at the spigot.
I'd like to get Jeff and John involved in the conversation. Jeff, do you want to jump in here?
You received a career award, and you're here in Washington, D.C., which suggests you're interested in policy. So I had a question relating to sort of the intersection of those two areas. And first, quick show of hands, how many people have tenure? Okay, so about half or do. But I was interested in if you were interested in becoming more active in advocacy, whether it is on funding issues, whether it is on diversity, whether it is on tech transfer and commercialization. Do you feel a limitation if you haven't received tenure, or even if you have? How much time could you spend away from the lab? How much do you need to focus on your research? And if the answer is a lot, where does that leave you and everybody else in your generation in terms of wanting to be more active on advocacy?
Jennifer?
I'll take a stab at that. I think what I'd like to do is first off draw a distinction between academic faculty, teaching faculty, and research faculty, because research faculty don't get tenure. We're not on a tenure track line. Most of us who are research faculty or research professors, it's a 100% soft money position. And so in the case of 100% soft money, where you have to bring in your grants for your salary, it is very difficult to break off and do that, because you're not supported by your university to do that. So you end up doing that on your own time. And so, yeah, I think we have to make the distinction there between academic faculty and research faculty.
Aaron, and then
I
Dave.
think essentially the answer to the question is, that we're expected to do research 100% of the time, and then for me, in a department where I do a lot of teaching, I do teaching another 20% of the time, and then I do service another 25% of the time, right? So the answer is essentially that these are critical things, but they're essentially on top of what we're mostly getting evaluated on. And so all of the strides that all of us in this room have done, aside from science, have primarily been as an overtime position, even though it's so critically important.
Dave, do you want to jump in?
Sure. I think the answer to question 2 is we would love to spend almost all of our time in the laboratory or doing related things that are interesting to us, and that can include teaching. But I think the reality is that whether we like it or not, and sometimes I love it and sometimes I don't, we need, as scientists in this country, to be better at telling our stories, because more funding isn't going to come from everybody complaining about there not being enough. More funding is going to come from us, from celebrating our victories. And everybody's going to want to invest in that when we're out there telling what we can do and educating the public and getting that buy-in. I think that's very possible. And we think we're all, we all need to do that, do a better job of that.
In terms of celebrating science and some of this, it would be interesting to look at how in some other places, scientists, engineers, that's what a lot of young people say they want to be when they grow up. In our country, a lot of young people want to be entertainers or sports athletes, or to really celebrate. And so if there were different ways to sort of celebrate science at the early levels on up, that would really help. And so one example.
We're doing that right now, Jordan.
Yeah,
This is the celebration.
No, right. That's exactly my point, though, because you see there'll be a picture with the president and then the group, and you see that circulate a lot around when it's a certain sports team, but when it's the team of scientists, you don't see this much. And so there are you just don't. And so we'll know, so groups like US First with promoting science and engineering and STEM fields, and then they make that more in like a sports competition where then children, from all different backgrounds and diversity get really interested in STEM and then compete in their robots battling in different kinds of events. And so there are initiatives like this, but it's something where it would be great if more of those exist and that it becomes really broad-based, where a lot of the public feels really enthusiastic about science all the time, not just if one specific event, oh, that's really neat, but just all the time. And that if things come from scientists, there isn't sometimes a dismissiveness in that science is somehow something that maybe doesn't fit with their worldview in some ways, to be sort of anti-science. And I think that's harmful for then policy if there isn't a situation where everyone is very excited about science and understands how it improves their day-to-day life.
Right. Erica, I want to give you a chance to jump in and answer Jeff's question.
Sure, thank you. Well, I like to sort of think of the advocacy that our role as an advocate is occurring through our science. So, for example, some of my recent work has been focused on veterans returning from the wars in Iraq and Afghanistan who all deployed there with PTSD. And these young men and women, they have an average age in our data samples in about their early 30s, and they're already showing these signs of premature aging at a cellular level. I'm talking about genetics, I'm talking about neuronal integrity, their overall metabolic health. And for me, that was really alarming when I started to see this very clear pattern observing from the data for these very young individuals. And that's how I want my advocacy work to show through, that I want to develop interventions that we can slow this process of cellular aging and help our veterans who have already done so much for our country.
John, you want to jump in?
Yeah, sure. Thanks a lot. Appreciate it. You guys are all obviously really, really smart, and I'm just a political hack. Talking about the presidential race, you probably look at it and you kind of shake your head and you're wondering what the heck is going on. But it actually has pretty big implications for funding as we go forward. And there's funding, there's basic funding, and then there's what you talked about, which is administrative burden, and kind of finding that. And I guess with Congress, having worked for Congress, they always want to have accountability, but they also don't know anything about science, which is kind of a problem for them. They don't understand the scientific process, obviously. Otherwise, they'd be scientists instead of politicians. So if you could talk a little bit about how you view the political process and how you think that you can get the right kind of balance between accountability and while easing those kind of administrative burdens, and then talk about the necessity, and someone talked about how important long-term funding is, as opposed to kind of episodic and kind of funding that kind of, and I think we've been through a fairly tough period with sequesters and things like that. So just talk about how you kind of, what your plan would be to kind of have sustained funding with kind of limited administrative burden with the proper amount of accountability. And
win the lottery.
It sounds great.
So the funny thing about writing a grant is that you have to say what you're going to do over the next 5 years. And of course you don't know, because it's, if you knew already, it wouldn't be science. It would be, engineering, implementation. And so, what tends to happen is people write that they're going to do things that they sort of already know how to do. Because if you write something that appears too speculative or too risky because funding is so tight, you're likely not to get the grant. I think a reasonable alternative model would be to fund scientists for reasonable blocks of time, say 5 years, based on track record. That is, if someone has done good science, up through their career thus far, it might be a safe bet to fund them with relatively few administrative burden, say for 5 years. And if someone decided, if suddenly I was out of ideas and became corrupt or something, maybe there's some small risk of that if I'm not reporting all the time. But the risk is relatively minor in that, at the end of whatever this funding period is, you could decide not to fund me if I hadn't produced good work. But I think that would be a model of funding that would allow scientists to spend a substantially larger fraction of their time on science, which is what they're supposed to be doing, instead of on the sort of administrative necessities of applying for funding and then reporting on the progress of research.
And there are some. My work has been funded by the National Institutes of Health, and they're playing with these very models, I think, for the very reasons Aaron is talking about. And I totally agree with that. And some other prominent scientists at my institutions once said, it's very important that you leave me alone for a while. And I think that is so true, because I think when you're talking about the risks of research, it's not just the lack of funding, but the US has actually been a really great place to do basic science for a while, but there's a sense that in a culture of more immediate gratification that they want answers sooner. And so a model whereby you do reward scientists for their track records, you do fund the scientists and not the projects necessarily, and let that go for a while, I think you have the biggest benefits in the end, but it's a hard sell. And I think you have to continue to really sell the virtues of basic research and patience in research.
Jennifer?
I was going to say one of the big benefits of stable long-term funding, Marcel brought up our declining student population. That soon as funding is tight, students are one of the first things often to be cut out of somebody's grant because students are expensive. With stable long-term funding, I think you would see a return in the number of students, or a stability in the number of students that we have to replenish the young scientists in the field as people are retiring.
I wanted to make an additional point, which is in the case of astronomy, the National Science Foundation, which is where I get most of my funding, funds not only investigators, individual investigator grants, but also facilities. And those facilities, some of them have been workhorses, have been working for decades, and then some of them, of course, we're developing now. And to get halfway through a fiscal year without knowing exactly what your budget is going to be when you're trying to build the next generation of telescopes it's crazy. It's crazy to have year-to-year budgets, I think, in a country this size, period. But it's particularly difficult then to do any kind of long-term planning. And if you want to be ambitious, it's very, very hard.
Which country is doing it right?
Well, I hesitate because the grass is always greener, and I don't necessarily. But I mean, certainly in the European astronomy context, a lot of the projects there are set out for decades, right? And so you can argue about the lack of flexibility, and there's a lot of things that we are able to do. I mean, one of the great things is that we understand this is the framework, and so we work within it, and people find ways to be innovative under restricted conditions. And the workhorse telescopes, they're still being used because people have found crazy ways to improve on technology that was 50 years old and do cutting-edge science, right? So that's fantastic. And maybe if you had a more long-term kind of plan where you knew, well, this is what we're going to build for the next decade, you wouldn't feel forced to do that. But on the other hand, it'd be nice to know, okay, we have the operating budget for the Large Synoptic Survey Telescope, which is the #1 priority for astronomy over the next decade. Right now, we don't. We have a construction budget, but we don't know how we're going to pay to run it.
Along those lines, to John's point, the question talking about federal research funding, in terms of your own research, what does well-funded federal research look like, say over a 20-year period? So imagine stability and federal support. What might we have? What could be the possibility of that type of support?
I would say, from the climate perspective, we certainly have our share of struggles when it comes to the political elements that weave into that. And I would foresee, with stable funding for 20 years, that we start to see progress on the scale as we've seen with weather forecasting. 20 years ago, the weather forecasts were significantly poorer than they are today. It's been demonstrated many times, and with climate, we're building the understanding to kind of extend our knowledge on those scales out to things like seasonal forecast, understanding what the summer may look like versus other summers, understanding what the sea ice is going to do this year versus another year, and that carries out farther and farther, and that's the sort of understanding we really need over the long term. So that's what I would see.
Erin?
In the area of infectious disease, one of the really critical factors that has resulted in the resistance that we see now and the lack of treatment agents is the fact that so many industrial partners have gotten out of the work because it's not profitable. If you take an antibiotic, you take it for a week. You don't take it for the rest of your life. And so if we had a sustained funding model, more academics could get into actually working on infectious disease without, and could actually make huge contributions that right now don't exist because industry has largely abandoned a lot of bacterial infectious disease work.
Raises a good question for me about the role of the private sector. And I imagine that there's some good sides and bad sides. So the good side is they got money. Bad side is they're worried about their latest stock price. Another bad side might be that they want to keep all the intellectual property for themselves. Could you tell us, what, and there's a big R&D tax credit that's part of this. How would you design that so that you guys get stable funding from both the public sector and the private sector?
You've been stumped.
Right now at the University of Minnesota, there are a number of programs that exist for companies to make partnerships with academics, and it largely stems through them giving unrestricted funds to various collaborative groups so that they can help research progress happen. In terms of how the intellectual property is managed, I don't have a lot of knowledge on that, but I know that there are agreements in place so that the researchers actually retain a lot of the intellectual property.
So sort of a common symbiosis that sort of exists between academic research and industry research is that industry tends to be focused on the near term. As you said, they've got quarterly reports and shareholders to satisfy, and ideally academic research should be focused on the long game. And back to your question, I think that if there was, in this dreamscape you lay out, unlimited funding for 20 years, what you would see is a return to focus on big, important problems. Because I think that one of the problems with the current funding model is that academics are also sort of beholden to quarterly reports. That is, if you take on a big risky project that might not bear fruit for years, then you're going to have trouble getting that next grant because you need publications to show for it. And of course that's important at some scale, but short-term research is exactly the kind of thing that industry is already geared up to do, and it might even be a better place to do it than academia because they've got all sorts of resources. The public sector research, the important hole that it fills in our country is doing that research that is going to help found the next big Google 10 years down the road, not 1 year down the road.
I want to jump back to a comment. I think it was Jordan, and forgive me if I have this wrong in terms of looking at my notes, but I think you mentioned we're losing some of our researchers to international headhunters, where some of our best and brightest are going overseas. Could you elaborate on that? This is something that we've talked about, but we're trying to get a better grasp about what that looks like.
So some other countries that do espouse these kinds of ideas, where if you find a really great scientist, you give them lots of space and lots of money and not a lot of administrative burden, and then let them be able to flourish the way they'd like, they find that then attractive to then go overseas and leave the US to have those labs. And that some faculty do this for sort of half the year and sort of split their time or they move fully over. And so I think that does create a brain drain of really key people. And as the funding gets tighter here and then more open other places, I think that would accelerate. And then what would also happen is then the sort of other world leaders, innovators, would be less likely to come over to the States to be educated and trained, because now you have those top people in their own home country, and then they don't have to worry about all these visa things afterward, and then there's policies that'll be conducive to that. And so I think we're starting to not be the magnet that everyone wants to come to the U.S. and stay in the U.S. Now there's other incentives, and maybe there's other places, and so it's kind of a more mixed matrix of decisions now. But the way the trends are going is that we might lose this sense of being a magnet, which I think would impact us on so many different levels we can't even conceive of, because we just sort of take it for granted that America's always number one in everything, in a sense. I mean the American public, and so that it doesn't need to be an investment made into science and engineering, that this isn't a crisis because, America's great. And so because there's going to be a lag between when we see that and where the investment needs to be made, which is now, it's something that I think we're not ready for, and it's hard to stop.
Real quick, a guy who's reported on this on Morning Joe and is now completely fixated on Donald Trump is Sam Stein. He's in the audience, and I want to kind of pull him in here to see if he wants to ask a question. Hold on a second.
Bring the microphone to you.
All right.
Testing.
Join the conversation, Sam.
That was totally unnecessary. So just to build off that, along the stage here, how many of you are contemplating going overseas and taking your work there? And how many of you have gotten overtures from institutions overseas to bring your work over there? 2 of you?
Yeah,
explain what they're offering and how alluring it is.
Oh, it's not. It's mainly because my wife is Canadian, and if it were up to her, we'd move to Toronto tomorrow. And I'm from New York City, so it's a little bit of a harder sell for me. But
yeah, then on my side, it's sort of being approached from Chinese laboratories. So they're very interested in the electronic materials we're studying. And sort of the approach is, you can come over for 3 months, we'll fund you, you will have set up a few graduate students for you, and then you can go back and, carry out your academic year at Northwestern and continue teaching. And it's to really set up a laboratory there and start training, their students. So that does happen. Yeah.
So I'd like to chime in if possible. I think it's really important to remember that immigration has, and immigrants have been the backbone of what's made this country successful, what's made this country great. I speak with a bias because I'm an immigrant myself. But even when during the awards ceremony, there was a list of how many countries the awardees come from at the very beginning. And it was amazing, and fostering that and bringing the very best talent internationally into the United States is what really has allowed us to succeed, and somebody mentioned to be the best in many, many things. And I think that's how we all feel. So if we lose sight of that, we're not going to have the premier scientific place in the world. We're not going to train the very best scientists. So I think it's crucial to foster keeping not only homegrown talent, but also recruiting international talent to stay here, to develop the next great thing, the Googles, the Apples, those companies, and help them really, really flourish.
Right. Jeff, grab the mic.
Question just along those same lines. You're all early career scientists.
Bring that mic in a little closer, Jeff.
If you could look ahead 30 years, 2 questions. One, do you expect that academic research will look pretty much the same when you're in your 60s as it does now? And if the answer is no, or if you are also interested in how likely you think you are to move into another setting, whether it's industry or something else, and what, if anything, that would say about the state of U.S. research?
I would say I certainly hope it's not the same. The statistics for underrepresented minority, for women, things are getting better depending on the field you're in, but for underrepresented minorities in astronomy, we still produce one African American PhD in this country a year, and that number hasn't changed in 30 years. You know, I refuse to believe that we don't have a deeper talent pool than that, and I think it's an outrage. And I certainly don't want to be part of a field 30 years from now where we're still producing one African American PhD in this country a year. So I think, you know, I've been trying to think of an analogy about this notion of giving, you know, what would happen if you could feed science the way it needs to be fed. And I think there is a kind of community analogy, right? When everyone is desperate for resources, your own self-interest becomes the primary driver. And I think that if you could fund the community in a sense that allowed the community to flourish, then you have this possibility to think about community-driven projects, and the self-interest is not necessarily the driver. And I would love to work in that community. I mean, you know, part of why I'm an astronomer is that I love astronomers. I think it's a great community to be in. But yeah, I mean, we suffer and we compete as a result of that suffering. And that makes it harder to have this sort of long-term thinking. Anyway, I certainly hope it's not the same when I'm 60 as it is today.
Erica and then Dave.
It seems to me that in the long term for the funding, where I work in the area of genetics, we need these large-scale consortia to really start to sort out, you know, who with which genetic variants is at risk for which conditions, and how then do we treat them in the realm of sort of personalized and precision medicine. And with stable long-term funding, we're able to collaborate and develop these broad consortia, not just across the United States, but I also try to collaborate with individuals in Europe and South Africa, all kinds of other areas, because we can't just solve the problem of whatever health condition you're studying in our little bubble. We need to really solve it more broadly, and the stable funding would allow for that.
Dave?
I agree with that point. I think the one way science is changing now and will continue to change is that it's becoming more collaborative. It's becoming bigger. It's becoming, in order to do some of the best science, it requires people from different fields and larger groups. And that's great, and I think we welcome that. One problem, I think, in biomedical sciences, maybe especially, is that institutions struggle with how to dole out credit and individual recognition for that work. It's very important when you're talking about tenure, as you brought up. It's a very individual thing, but the collaborations in the larger scale science works better when it's the entire product that's valued, and when successful collaborative work can be a metric in and of itself. I think the better we do that, the bigger questions we'll be able to answer successfully.
And I'd like to contribute just a slightly different perspective on this, perhaps. So I sit at a cooperative institute where I'm a University of Colorado employee, but I work with NOAA directly, Department of Commerce, and certainly the kind of mission-driven side of that does play into what I can do at the university, but it also provides some of this kind of bigger picture thinking, collaborative thinking into the mix, where we have a specific set of objectives through that institute, through that agency. And so in some ways that's the best of both worlds, and in other times it can be a bit of a nightmare to work through all of the logistics of making both sides happy. But it's certainly, in this sense, it's very productive from the fact that we have a set of objectives that we have to try to tackle, and can kind of stretch that from a university perspective and be on the innovating side of that.
Tessa?
Yeah, I really like all of these answers, so I'll just add that I think academic research and academic institutions change because we ask them to. And so at times when I'm really frustrated with this system, I remind myself that I'm part of the system, and we need to ask it to move in these directions where we're asking really big, important questions, and including all of the people that we can possibly include, because we're responsible for that change.
Jennifer?
One of the big things that I've seen in the evolution of my career, I'm going to look at it from a top-down perspective, is from the perspective of the funding agencies. And the evolution I've seen is that more of the federal funding organizations have acknowledged that there are societal problems that we have that they don't have the money to support right now. And the way that they're trying to do it is they're bonding with and connecting and collaborating with other federal organizations. So in the underwater world and in the ocean world, we've got the Navy, NSF, NOAA, Bureau of Ocean Energy, management, USGS, all have very similar problems. In my case, the sound problem is all of their problems, and it's really nice to see the funders coming together to fund that particular question. So I think 30 years from now, if the fiscal climate were to stay as it is, you're going to see more collaboration between the federal organizations for a common goal.
Great. And with that, we conclude today's discussion. Again, congratulations on being the 2016 PECASE Award winners. Thank you for joining us. Thank you for your support of the Science Coalition. We covered a lot of interesting ground today, and I want to say a sincere thank you to all of our guests who've joined us. And with that, we're done.